Hey, good morning, everyone, and welcome to Fine-Tuning Your Embedded Model for Better Search, learning from Agentic Search at Dell. My name is Rachel. I'm a part of the UBC ARC team supporting research engagement and training. We're really glad you could join us today as part of the 2026 ARC Summer School. Just a quick note, the session is being recorded and will be uploaded to our YouTube channel. And a few housekeeping notes before we get started. Please use the Q&A or the chat feature if you have any questions. You're also welcome to submit questions anonymously if you prefer. A quick reminder that to comply with UBC's privacy guidelines, external AI transcription or recording tools are not permitted during this session. We appreciate your help with that. Before we begin, I also like to acknowledge that UBC's Vancouver campus is located on the traditional, ancestral, and unceded territory of the Musqueam people, and UBC Okanagan is situated on the lands of the Self-Okanagan Nation. Grateful to live, learn, and work on these lands. I'm now pleased to introduce today's instructor. Rachel is an applied AI scientist and distinguished AI engineer with over 7 years of experience translating cutting-edge AI into real-world impact. She specializes in LM-based knowledge retrieval, multi-agent systems, and deep learning for time series data. Rachel leads end-to-end development from data curation to the system architecture to prompt engineering, model training, evaluation, and production development. Rachel holds a Bachelor in Science in Mathematics and MBA, and also graduated with honors from Yandex Elite Machine Learning Program. We also have Lori from Dell, who will be assisting with the session today. And with that, I'll pass it over to Rachel.
Thank you so much. Let me share my screen. I'll move into a presentation mode. Okay, so I guess it was a nice introduction, so I'm not going to say a lot more, just a little bit maybe about the team I'm part of. I'm part of an internal AI solution team that develops internal products for Dell, meaning we are working on AI products, and our users are normally Dell employees, and we are going to discuss part of the work we are doing today. So at Dell, the work I'm leading is an agentic search, meaning we have R&D teams that are searching information in GitHub, Confluence, Jira, SharePoints, technical documentations, and all of that search is done through our engine. Now, one thing that we have noticed that for the semantic part of our search, there were some or many questions that I can categorize maybe that we didn't answer correctly. And here are some examples that are from real life examples of users that are asking questions that we just didn't get it right. And when trying to think of it or understand the type of question, we have noticed that those questions are using a Dell internal language, internal terminology, acronyms, internal products like Cloud IQ, PowerScale, Power Protect, a relationship between different products. That is kind of a knowledge that is in the world of Dell and not something outside. And this is a motivation for my talk today, to understand what do we do with that. So we are going to discuss why embedding models are important and what are the common training methodologies. We'll discuss a little bit of the common use cases and when it's a good time for training your model. We'll present the common loss function and understand its beautiful mathematics. Talk a little bit on what our work, the use case at Dell, data collection, and how do we evaluate results. And just before I start, I will make a pause from every section, I guess, to answer any questions you have. So feel free to ask anything. I would love it to be interactive. So embeddings are, let's say, humans understand words, machines understand languages, and embedding models are the bridge They can represent words and sentences in a semantic way that will, when pieces of text that have similar meaning will be represented closer on the embedding space. As you can see here, if you have pieces of text that has to do with password or login or account, they will be closer to each other. Cities and countries will be in a different way. Anything that has to do with running in a different place. It's a simplistic, obviously, representation, but just to get the meaning of it. Let's talk about what are the most common use cases for embeddings. So I think I would say number one would be information retrieval. You can see a lot in the industry. Yes, you can see a lot of companies that are doing RAG, retrieval augmented generation. And embedding is used for that. Classification, where you assign categories or intent on topics based on semantic context, is the second thing. One example would be when you are want to categorize your incoming emails, spam or not spam is a naive example. And if you want clustering, if you want to, you have a lot of data and you want to make sense of it or cluster it into similar areas, like if you have user queries and you want to see, maybe we have some similar user queries and dissimilar user queries, clustering is a good way. And recommendation is also one area that is using extensively embedding models, for example, for personalized recommendations. So I think one more important thing is to understand the process of training. Now, I just want to say that I'm talking a lot in the context of open source, and because most of our work at Dell is we're using completely open source models. Yes, not training with an API from OpenAI or Anthropic. It's completely on-prem on Dell's hardware, and the models are open sourced. So the first stage normally is a pre-training, where you take what we call a chunk of the internet, everything that exists publicly, books, Wikipedia, public GitHub repositories, everything that you have there, you take it in, and the purpose is to teach the model a general understanding of the language, connections between words, a little bit of grammar, syntax, but not the actual fine-grained semantic meaning. And the way to do it, or one of the most common ways to do it, is masked language modeling. This is where, when you have a sentence, you mask one word, and you let the model guess the word you wanted to guess. So this is, when this stage is done, is normally on billions of tokens. It's a lot of data, massive data. And it's very, let's call it unsupervised. The data is normally not supervised in the way no one is actually cleaning it or taking care of it. It's just massive amount of data. Now, for the second stage, which is to kind of get the model into a better place of semantic understanding, one of the most common methodologies that I'm going to talk about today is contrastive learning. And this is where you are collecting very high quality data. Usually it takes more time and more effort because this data needs to be really high quality. And in the case of contrastive learning, we usually collect pairs or triplets of examples. Let's take a look at an example. For one triplet, let's say, would be a sample of the data, would be a question of the user, how to reset my password, then a positive answer, what are the steps to reset your password in your account, and then one negative answer or a few negative answers, like best beaches in Hawaii, completely doesn't answer it, right? And the idea is, when you train, is to make the query and the positive answer closer in the embedding space, and the query and the negative answer further apart in the embedding space. So to create this similarity, this semantic understanding of what is closer to each other. And how do you do that? Like by training. I think it's worth going over the loss function, which is, I think, beautiful and not very hard to understand. One of the most common loss functions are info NCE, is the information nodes contrastive estimation. This is, if you read papers on contrastive loss, you will see normally this loss or a different version of it, but it will be kind of the same idea. So the idea is that we take a batch of questions and positive answers. Let's say we have a batch of 100, and then we use the log loss where on the top we have the exponent of the similarity, S is for similarity, of questions and positive documents, and on the denominator we have the positive similarity, but here we have a sum of the negative similarities, and we treat, when we have a sample of 100 questions and answers, positive answers, for each question, we treat all other documents as negative answers. And the point or the goal of the loss when we minimize it is to increase the similarity of the positives and the questions and decrease the similarity of the negatives and the questions. And you can think of it as the denominator contains the same positive pair with all other competing documents. And we want the positive document to kind of dominate this competition during training. And we want this similarity to be as higher and also smaller. And here I put it again. I think maybe with taking a look at the geometric view of it, okay, of the log loss of similarities. If, let's say, before training, we have, let's take a look at a sample of, again, how do I reset the database password, and I have a positive document, and then I have a few negatives. And if before training, I see the similarities and the distances between the questions and those vectors is roughly, let's say, the same, then I would want after training that the similarity of the question and the positive document and the question and the negative document to be, negative should be further, as you can see here, and that should be closer. So point is high similarities for positive, low similarities for negative, and you achieve that by minimizing the log loss of this expression. One more thing to talk about when we talk about training. It's the prefixes. So prefixes are meant to resolve conflicting reward signals. And what do I mean by that? Remember that we talked about different use cases for embedding models. It could be clustering, or it could be information retrieval, retrieving answers based on questions, or clustering data. And when you have a model that treats all of these cases, it's a general model, how do you deal with different tasks? So for example, if I have this question, what is the capital of France? And what is closer in meaning to the question, number one or number two? So number one is just a different version of it, and number two is the answer. So if I want to know what is closer, I guess I would say it depends on the task. If I'm doing a task of, let's say, clustering, right? I want to cluster the sentences that have the same meaning, I would say that the question and number one are closer to each other. But if I'm doing a different task, which is questions and I want an answer, then I would say that the question and number two are closer to each other. So how do you handle that when you train? The answer is prefixes. When you train for different tasks, you put a prefix before the sample, the text itself. For example, here you put clustering as a prefix, and then the question, and then clustering and the different version of the question. And these prefixes are giving signals to the model on the type of tasks and the type of and it will change a little bit the embedding according to the task. Same goes here. What is the capital of task? You put a prefix of search query, and then you put a prefix of search document. And this is telling the model, okay, this is a signal for a different task. So once you put when training is finished, then potentially or hopefully you will get different embedding for this and for this. Maybe I will pause here to see if there are any questions, because I think what I cover now is a high-level description of embeddings and training. Not sure if there are any questions. I think there are not, right? I don't see any. So if all good, I will move on. Looks like everything is good. Okay. So let's talk about the agentic search at Dell. We build a search engine that is searching. It's primarily, in the past, it was kind of a chatbot, right? That is aimed for R&D teams, architects, developers, technical writers, product managers that needed to search information in Jira, Confluence, GitHub, GitLab, SharePoint, databases. And we did a little bit of a pivot because we understood that this is the way people are requesting context is not through a chatbot anymore, but rather engineers need context when they program in their Cloud Code or Windsurf. And when you have an agent that needs to solve a bug and it needs some kind of a context layer from Confluence or from Jira, then Cloud Code will go and fetch the information for the user. So we started it 2 years ago, and half a year ago we pivoted and say, okay, we are not for humans, we are also for coding harnesses. And we are very much API based. So we have MCPs, okay, and we have skills that you can put inside your Cloud Code or Windsurf, and it will work from there. But what is it? What do we have, basically? So I will talk about the architecture, which is basically an hierarchical architecture, which is an agent that routes to a different agent in order to provide information. We have the part of semantic search, which we will be focusing on today, and domain adaptation with training embedding models. We are doing memory management, and of course, this system is permission aware. Permissions to different sources of data is very important at Dell. Some real life example, what do users are asking in our system? So they are asking a lot about bug solving, onboarding, where can I find a guide to setting up a virtual machine, questions on testing, questions on technical configuration, and some questions that are kind of how do I do this or how do I do that at Dell. And this is the architecture, the hierarchical architecture I was referring to before. The way we build it is that we have what we call a supervisor is an orchestrator. Any question that is coming to the supervisor, and the supervisor routes that question to the sub agents that we call. We have a Jira agent, which is an agent that is using different JQL tool in order to query data, find similar tickets, summarize issues, anything that you can do in Jira with an API or JQL, you can do it within that agent. Confluence agent is the same, using the API to fetch information, grab information on the writers of this page, or anything you can do with an API. We defined as tools. GitHub is the same. You can search for PRs, you can search for code, read the complete files, and other tools that are GitHub related. Semantic search is a workflow, which is the part where we ingest all the data in advance. And when you ask a question, then we send a request to a vector database, and we try to fetch information based on cosine similarity. Once we get all the results, we filter them with a re-ranker and provide back the results that we got. We have some security agents that are making API calls to OSs like SUSE and Ubuntu. And DB agent, this is a bit experimental, that can make SQL queries to databases at Dell. Just one important note, the reason we created it is because it's limited context and limited responsibility for each one of them. They all can talk to the supervisor only, not with each other. And the idea is, once there is a question, supervisor send request to one or a few of them, they return an answer, supervisor decide, do I need more? If it needs more, it calls again. If it doesn't need more, it comes back to the user. And of course, this whole flow is limited to a few turns. A little bit about our architecture, or how does it work. So we have a web application. It's a chatbot where you can go and chat to your data sources. We are API first, and we are part of code harnesses like Windsurf or Cloud Code. And it is defined as a skill or an MCP there, and this is invoked automatically when users are working within their Windsurf. Now, our backend, except for the architecture that I described before, we have a few other components. Langfuse is what we use for observability. Everything that, all the agency interaction, the tool calling, everything is saved there. The models that we are serving, that we are using, the LLMs, the embeddings, and the re-rankers, these are just examples of what we are using. But we have two guidelines. One, up until a month ago, it was always open source, meaning you can download it, for example, from Hugging Face and put it on our own infrastructure. This is important because of privacy. Dell does not allow to expose private data outside. Recently, we started experimenting with Gemini and Sonnet, which are kind of private instances for Dell. We have PostgreSQL, where we save all the chats information inside our system, and a single sign-on for authentications of all of our users. Another important thing, and this is related to the work on embedding, is what we call auto data ingestion. We call it bring your own data. Users that wants to create, let's say, their own bot. Let's say I'm working on 2 repositories, 3 Confluence spaces, and 1 Jira project. They just put in the links, and then we have a job that works behind the scene that cleans the data, chunk it, and put it into a vector database. And within a few hours, it is ready to query. The bring your own data architecture, again, is, I'm not going to go all over the details because it's a lot. I'm going to focus on Confluence a bit later. But Jira, Confluence, GitHub, and SharePoints, we work with semantics chunks and code splitting, detecting more than 30 languages, and using AST. we use different embedding models for different sources, and I will talk about it a bit later. And one important distinction is when we talk about code repositories in such a big companies or on Confluence, then it's changed a lot all the time. So we have an auto update job that just check for changes. For example, in Confluence, if we detect a change in the past 2 days, we just take the page, reclean it, re-embed it, and put it in a vector database. So it includes it all. We chunk it in advance, and we put it in a vector database.
Rachel, we have a question in the Q&A is the arrows in the diagram are connected via NCP? That's the question.
Wait, let me read the question again. So the arrows in the diagram, are we referring to this diagram or which diagram? This one? Let me talk about an MCP. If we talk, I'll try to answer and you can ask again. So if we talk about what the agents are using, we are defining our own tools. We are not using any MCPs. The only MCP that we have is we wrap our own application in an MCP that other people are using. So other than that, there is no MCP here that we are using. I assume that this one could be with an MCP, but we are not using. Each Jira agent is, we define our own tools and functions, and the agent can consume those tools by tool calling, but not through an MCP. I hope that answers the question. Okay. So I want to focus on Confluence because the training that we did, training embeddings, was on Confluence only. This was experiment, and we wanted to try it. Confluence was a bit easier than doing code, so we started with Confluence. The way we fetch Confluence is, first of all, we use an API we do it space by space. Yes, API to get all the pages. Then you kind of reformat it to an HTML and with all the ancestor and metadata that we have on this page. We filter a lot of there are a lot of text that is related to Confluence widgets, so Confluence specific stuff that doesn't have any meaning. So we need to filter a lot of data. Also emoticons, avatars, alt text, all of those are kind of things that it's classic data science, data cleaning stuff. And then we convert the HTML to MD. One more thing that is important is tables. Tables are a big challenge, right? Because when you take a document, you want to detect the beginning and the end of the tables, and some tables are not as easy as 3 columns and many rows. You have a very complex structure of a table, and we worked hard specifically on tables only. We do also attachments, meaning if you have attachments in Confluence, like images, Excel files, PDF, Words, everything, we take, we read, we clean, and we chunk. Then after it's ready, we chunk all of it. It's table aware, meaning if you have a very, very, very long table, how do you chunk it? So we normally do it with keeping each chunk contains the name of the columns and is aware of the fact that it's from the same table. And then we embed and store it in a vector database. We use PG vector for that. So this is what we do in Confluence, and the reason I explained is it's important for later. So if we go back to the question that I think I started with at the beginning of the lecture, is why why fine-tuning your own embedding, right? So many questions that has to do with internal products or questions that are using internal language of Dell, like abbreviation or acronyms, or on Dell specific workflows, like the internal enterprise language, is something that we figured out. It was a hypothesis that this is why we can't get the right result when we are using out-of-the-shelf embedding models and doing semantic search. Now, when I say it's an hypothesis, it's because when you do semantic search, many things could go wrong, like many things. It's a long process, the chunking, the indexing. There are a lot of reasons why it cannot succeed. And one of the hypotheses for us was, okay, maybe a model that can understand Dell's data better by training it would yield it better results. So, and this is kind of a summary that says if you're looking for signals for domain adaptations, then you normally ask yourself, right? Does my data look different from the data that the model was trained on? And normally, when in the context of open source model, majority of the models are, they release, or at least saying what was the data the model was trained on. And you can also take a look on the benchmark that, and which data, the benchmark that they are showing, and is it relevant to you? Okay, so what else did we do in order to check or to understand if the model is working for us? Every model that is coming normally with a vocabulary. Vocabulary is a set of tokens that the model have seen. And I wanted, now, what happens when you train a model, or not even train, what happens when you inference with a model and you put a word in that the model have never seen before during training? Normally what happens is that it puts the UNK, unknown token, it's called. The model just puts there the unknown token. Unknown token has an embedding of its own, and this is how you roll. So I wanted to see how many unknown tokens do I have in my data. What does that mean? I have the tokens that the model have seen because they publish it, and then I went to my data. I started tokenizing it, and then I checked token by token. Is it in the model vocabulary? Is it not? And then I discovered all the tokens that are not in the model vocabulary. Sorry. And here are some examples. Emojis, for example, were not part of the model vocabulary. Unicode or box drawing, like these ones, this is things that the model doesn't know. And I guess it makes sense. It's a lot of noise. Or Kubernetes or Helm symbols or check marks or long camel case compound words. So that gave me kind of an understanding of the things that I'm seeing here. Are they important enough for me to try to think maybe I should train from scratch with all the new vocabulary at Dell? And the conclusion was no. These are okay. We have a few tokens here that the model doesn't understand. They are not important enough. I will not retrain with emojis. I don't think it makes sense. So the decision was, okay, we need to fine tune. There are some unknown tokens, very small ones, not important ones. So we will focus on fine tuning in order to make the model and hopefully understand better the semantic meaning of Dell data. I can pause before I go into how do we choose the base model for training, if there are any questions. Okay. So how do you choose the base model? When you work in an enterprise environment, the first thing you do is, of course, look at license and commercial use. If the legal team of Dell doesn't approve it, we can't do anything with it. So you cannot choose any model without the right legal approval. That's the first thing. Second thing we look at is how open or how reproducible is that work. And when I say open, I'm not only referring to open weights of the model, right? Because if you're using open source, all of them have open weights, but also to the training data and the data itself. Did they release the data that they were training on? That's important. We take a look at benchmarks as well, right? I want to take a look at benchmarks with the tasks that are relevant to me. If I'm training a model to be better at retrieving information, questions and answers, then I will look on benchmarks with the task of retrieval. If I have code or retrieval for code, so I'm going to take a look at code dataset. Inference costs and latency is also important. Like, what's the size of the model and how much does it cost for us to inference it? Like, what is do we need 1, 2, 3, 4 GPUs? Multilingual support, sometimes we need more than English, and context length. How many tokens can we put at once is also important. So we ended up that was back a few months ago, and every time we reevaluate with EmbeddingGemma by Google and Nomic Embed by Nomic. Their commercial use and licenses were approved. Of course, that was the first thing. They were both open weights, but it's Nomic is extraordinary. If you are interested in trying to train or fine-tune yourself, take a look at Nomic website. They have extraordinary GitHub repositories with all the data, all the training code, everything, with, of course, the papers. Both of them are tiny models, so that was fine. EmbeddingGemma was, in terms of context, was smaller than Nomic Embed. And also supported more than one language. Nomic Embed, as I said, was extraordinary in reproducibility, and EmbeddingGemma wasn't that much. And we decided, first of all, what's the best fit for Confluence? We decided we'll go with embedding, with a Nomic Embed, because of a longer context. We wanted a longer context for that, and it was pretty good model. And Gemma was very good with code retrieval. So we took Gemma for coding. And this is a part that I want to talk a little bit about how we are prepared the data for training, and I'll provide examples. I can pause again if there are any questions. And if not, I can continue. Okay, so how do you prepare data for training? So you start, remember that we have ingested a lot of the Confluence data, all of the Confluence data of Dell in advance in a vector database, right? So this is a chunking part where we already discussed. And then once I get a chunk, I want to create this for this chunk examples of questions. So I let an LLM do it. And an LLM started with creating for me 3 questions per chunk. After I did that, the question is, okay, so how do I create negative examples? So for creating negative example, I took a question and then I sent it to the vector database in order to fetch or to retrieve chunks that might answer this question. But this was with some limitations. We limited the similarity to be larger than 30%, but smaller than 80%. So in this range, you hopefully get candidates that are not exactly the right answer or best answer, but maybe a similar answer, but not exactly answering it. And we also checked that if the positive chunk is inside and removed it. Then out of it, we kept 7 negative and built a sample. A sample would be a question, a positives, and 7 negatives. And let me show you an example, okay? So let's say I have this chunk, a passage that say, to install Windsurf on Ubuntu WSL, then first you need to install it, blah, 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 blah. Okay, first stage, I requested an LLM to generate for me questions on this passage. So I have, how do I install Windsurf on Ubuntu? Or how do I connect Windsurf IDE? How do I use Windsurf with Ubuntu? It makes sense. You take a look at those three, makes sense as a question to this passage. Then the positive is this passage. This is a positive answer. And then you go and you grab 7 negative answers for each. And each one of them is one sample. I hope it makes sense and it's clear. And if not, you're welcome to ask any question. Okay, a little bit of exploratory data analysis on our samples. I cared about the number of tokens each one had. So the distribution of tokens, for example, for the question was like kind of max 50 tokens per question. If we take a look at the distribution of the positive answers, we had max 1500 and roughly kind of the same for the negative answers. So it altogether, it's just a sanity check to make sure that, okay, not seeing like answers that are completely very, very long or very, very short. And on the bottom, I wanted to check the cosine similarity of the question and positives and questions and negatives. And I wanted to see the distribution of it and to understand what's the overlap that I have. And you can see here in red are the negatives, similarity distribution of question and negatives, and similarity distribution of question and positive are in green. And they have a pretty extensive overlap, I would say. So my expectation was, okay, if I train, I would want those two distributions to be further apart. I would want to take the positive distribution to the right and negative distribution to the left. That will tell me that I have kind of a good separation. My point is to separate the positives from the negatives. So before I started fine-tuning, just let's say a little bit of a nice story. You know, in the past, or if you guys have trained models in your lives, though I think that 2 or 1 year ago, up until 1 year ago, the way I do it is normally you train an LLM or a deep learning model, you set up some parameters, right, like learning rate, batch size, etc. You train, and then you try the training with like different set of parameters. And then I think it was two months ago that Andrei Karpathy, he kind of had a nice tweet on his auto research idea. And that idea said, let's provide an MD file. Let's write just an MD file to Opus or any other strong model, and give it instructions. And these instructions were, I have a training loop called train.py. I have configuration file. Please, you are allowed only to change the training and the configuration. And please play with whatever you want and make experiments. Every experiment that you train should last 10 minutes. And then you check the loss and accuracy. If the loss goes down, then we keep the parameters of that experiment and commit them, and then start another experiment. So I thought I did the same. I kind of prepared a very long file instructing I think I used Claude Code with Opus 4.6, and I said exactly the same thing, save it all. do experiments of 10 minutes and ran it overnight. And overnight, it was performing kind of 135 experiments. I took a look at what they did. Some of the things were a bit stupid, but I chose one experiment that looks well, and I started running, and I said, okay, this looks optimized. It saved a lot of time. Let's start with those parameters. So I started with those parameters and let it run on the training for a few, I think, 2 epochs. And let's talk a little bit about the setup of distributed training. First of all, I was running on 4 H100s. The number of negative per question was 7. I used a batch size of 128. And my training data included all of the confluence, most, not all, the confluence spaces at Dell. It was around 9 billion tokens. Okay. Are there any questions? Should I pause? Okay. So let's start with how do you do this? Like what happens when you do distributed training on 4 GPUs? First stage is the data loader, right? We have 4 GPUs, and if my batch size is 128, it means I have 128 questions, right? But I also have plus 7 negative answers and 1 positive answers. So I'm adding to those 1024 documents. So each GPU is now seeing 128 questions and around 1,000 documents, each one of the GPUs. Then we move to the second part, which is a forward pass, right? We put in the text. What do we get back? Vectors. Now, there is a trick here to save memory. The first one is we are not saving the computational graph. With PyTorch, saving the computational graph, meaning you're saving the whole activations and different parts of attentions on memory. And it takes a lot of memory. So this was not saved here. And the second thing they did is putting in everything in a batch size of 32. Every time they put 32 documents, got the embeddings and so on and so on until it was finished. All of that in order to save memory. So we put in questions and documents, and now we ended up with vectors. Each vector has a dimension of 768. So questions embeddings resulted in a tensor of 128 over the dimension, each one of them. And the embedding we got from the documents were 1024 over the vector dimension. I hope it's clear so far. I think it's a little bit interesting to see how it works behind the scenes. And if you have questions, feel free to stop me, really. So now you do the all gather. What does it mean all gather? All of the GPUs are now getting all of the documents and on their hosting them all. So now you have actually, if we have on each one around 1,000, now each GPU is seeing now around 4,000 documents shared on GPU. So now each GPU is holding a tensor that is 4,000 over 768. Okay, so remember the loss. The next stage is we want to perform the loss, right? Remember the loss function, which is an exponent of similarities, and the similarities are supposed to be between all the vectors to all the vectors, basically, right? All questions to negatives and questions to positives. So here you can see this is the tensor of the questions, 128 questions. Each GPU is comparing those questions to all of the documents that exist almost 4,000 documents, and performing similarity between all of that, and then putting it in the cross entropy loss. So why it is stronger than just comparing if we have a batch of 128? Think about it that each question has one positive answer, and all the rest of the documents that are not the positive answer are becoming the negatives. So now the model, when it's training, it has to separate one positive against almost 4,000 negatives. It's a harder task. If you succeed in that, it means that you have a model that performed a better task. Separating one positive to other 4,000 negatives is hard. So this is where you calculate the actual loss after you had the embedding, and then you do, there is a little bit of a trick with grad cache and the surrogates that I won't get into right now, but the idea is we calculate the gradients, and then once we calculate the gradients, we average them, and we update the model weights. And when I say update the model weights, each model is deployed on each GPU, so each model is updated with the same gradients. Okay. So I think for the training part, I was putting a focus on how we prepare the data and a little bit about the how is distributed training treating the samples. And I want to move to evaluations. I think, where are we on time? I think we have 8 minutes left, right?
That's right.
Okay. So, okay, 8 minutes would be fine, unless anyone has a question. Okay. So, remember the similarity distribution before training, and I told you that my goal was separating those. So this is before training and this is after training. You can see that there is a better separation now. Better separation means the similarity between of the positives and the questions and the negative and the questions has moved a little bit or is now more separated. It's not perfect. There is still an overlap, but much more separated than before. And this was the first signal that told us, okay, maybe something worked here. But this is an application, so what I really want to check is the quality of the answers. So the evaluation setup was, we had 300 SME verified questions that we tested against. A question would be, how do I get WinSurf access? And then you get expected sources as links. And what we check is recall at K, meaning I want to check when I retrieve an information, do I have the right link or do I not have the right link? And when we compare the fine-tuned model versus a non-fine-tuned model, we saw that there is an increase in all of the experiments. There is an increase, at least of 10% of getting the right sources for the answer. One more thing to check is a downstream task. We wanted to check with an LLM as a judge, question to answer, meaning does the answer is related to the question? And does the answer match the ground truth? And we checked the answers for the whole system. Then we saw a little less increase, but we still saw an increase of 4%, which is considered a good experiment for us. One last thing to mention is the monitoring. Monitoring means that, okay, this data is changing very frequently when we are talking about Confluence, GitHub, Jira. So one thing to check is how quickly does the data change, right? If after 1 month I see that we have 1 million or 2 million new pages, this is already a good reason to start retraining. The second thing is to check for data drift. This is a more classical one. You check the data distribution in production against the data distribution of your training data and see what is changed. And we also check system quality signs, degradation. For example, people can usually or normally provide a thumbs up or thumbs down in the website. And we also check if people, when we are providing answers, we provide also the links to the sources, and we check the rate of clicking on the links and if that has changed. And I think it's time for summary, or at least for what I would hope you would take away from this lecture. I think that embedding models are beautiful. They are normally overlooked, and I wanted to highlight the way you train and the loss function and when fine-tune is needed, and to give you a bit of a peek of how we did the training and how do we monitor it for real use case at Dell. And there are a lot of things you can do on your own. If you want some links, I can share it later. And that's it. I think one more thing is for you guys is if you want to join the Dell Technologies AI Day, this is your chance to scan the QR code and join. And other than that, I guess I have to say thank you. Right, it's not moving to, and I have a thank you slide, but it's not moving there for some reason. Oh, here it is. I'll do it manually. So thank you, guys.
Thank you, Rachel, for such an informative session. I just want to highlight that we have a few upcoming sessions for summer school, including a session with another session with Dell Technologies this afternoon on physical AI. So definitely go to our website to check it out. Also, I'd like to invite you to complete our feedback form. We would love to learn how we what would you like? What can help us to improve future sessions? It should take less than 3 minutes to do, and you'll be entering into a draw for a $20 Amazon gift card. I just entered the link in the chat. Yeah, thank you so much. And I have enabled everybody's mic, so you have any last minute question for Rachel, feel free to unmute yourself and ask her directly.
Hi, yeah, excellent presentation, very informative. I was wondering when you selected Gamma and Nomic, how do you arrived in those two models and later discussed with the legal team? That's a different step later on. But how did you arrive in those two models? There are many models out there, right? Like, what were your thought process and yeah?
So I think that normally, like I follow industry trends, right? There are always new kids in the block that are really good that are kind of stars on the leaderboards. So I would say that this is my first thought process. And I know also what do I need to eliminate exactly. For example, I'll give you, I'm not looking at models that are kind of are based in China just because it's not allowed, but they are really good. So first of all, I take a look at the leaderboards. I know what I need to filter according to Dell, yes. And then back then, a few months ago, Gemma, and I'm looking also for tiny models, yes, because we need very fast response. And back then, Gemma and Nomic had really good scores on all the leaderboards. So I had a few other ones in mind, which I don't remember the name, but I can share it later. Two of them fell on licensing that I wasn't aware of, and one of them was just not good enough. So this is the beginning of it, right? Once it goes through the licensing stuff, then I really take a look at the data if it's available. I care a lot about the data because I have code and I have technical data. So I want to make sure that those models were trained on code and technical data as well. And that are the basics. And then you just, you try it. We make a lot of experiments for it without training, yes? Just to see, we have a a benchmark. So we can test those against our benchmark and get like a real sense of, okay, it was really good on the benchmarks on Hugging Face, but is it good for us? So this is the process normally.
Thank you. You're mentioning something about the little bolt, or maybe I missed it. Like you were mentioning you looked up in little bolt to see the benchmark of the model. I did not catch the word.
Hugging. You mean what do I look when I take a look at the model? So what
Yes,
do I search for?
Yes, yes.
So leaderboards are kind of every model that is released is releasing the scores on different data benchmarks, right? And there are in Hugging Face, maybe I'll share the link here. In Hugging Face, there are leaderboards specifically for embedding models, which gives you basically, here is the name of the model, here is the benchmark it was test on, and this is the score. So I think it's called the MMLU. It's let me share it here. Wait, I will share it later on. I can find the link now. But once you see the link, you understand. It gives you all the information on in the leaderboard. Here's a model, and that model was, when it was tested on a specific database, it was very, very good.
Got it. Thank you.
Yeah, oh, here I found it. It's called the MTEB leaderboard. I put it here in the Teams. You can take a look. And you will see lots of models and their scores for different tasks. For example, a score, how did they do with retrieval? How did they do with clustering? Stuff like that on different data sets. So the link is here. Cool. Anyone else? And by the way, feel free to, if you have any other question you want to consult about training or anything else, feel free to reach out over email. I'll send my email here. Be happy to answer any questions. Rachel@dell.com. Okay, great. So thank you, guys.
Thank you. Yeah, if there's no other questions, I guess we'll close here. Thank you so much again, Rachel, for a great course, and everybody have a great rest of your day. Thanks. Bye-bye.
Bye-bye.